right, good morning, everybody. Welcome to Chemistry Week. Today, the chemistry department is conducting a bunch of reactions that are famous kind of online. We're going to be doing it, one with each teacher and members of the Chemistry Society. The one we're going to be doing today is the dichromate volcano with a little twist. So here's the reaction right over here. We have ammonium dichromate, which is this orange compound, which we're going to have. You're going to see it's made a little volcano here in the fume hood. So if you can just take a look, you can see this orange dichromate. It's very, very toxic. We tried to make a Jeju diorama, so it's a shield volcano right over there. And what you do is when you give it some heat, it will combust. And you're going to get some nitrogen, some water. It's going to be super hot. It's going to vaporize like that. And you're going to make this chromium-3 compound, which is less toxic and go green. So hopefully when the volcano erupts, we'll make all this volcanic soil, and then it'll go green at the end, and we have our green Jeju. Usually we light this up, usually with some activation energy, we just give it a little light. But we're going to use another chemical reaction. We're going to use this thing called manganate. It's this beautiful purple powder right over here. And it's a strong oxidizing agent. So what we're going to do, we're going to put a little bit of glycerin on it, a little bit of fuel. So think of this as burning also. So fuel plus oxygen equals combustion, we get energy. So we put some of that at the center of the volcano, so making it like a little caldera in the middle. So when we add the glycerin on like that, it should give us enough energy to, boom, ignite the volcano, blow it up, and then make Jeju green again.
Hello, we are Jane and Alan and Aiden from the Chemistry Society, and we would like to introduce about the safety cautions. First, we place the heat-proof mat in order to prevent the fire spreading out through the chemical fume hood, and
we place aluminum foil over the box to prevent the box catching fire since aluminum has a high melting.
And we place this plastic in front of the box to prevent any kind of fume or kind of powder coming out, which is considered toxic. And actually what happened yesterday is that we used some kind of type of plastic called
Vinyl acetate.
Yeah, and like that actually kind of burned the entire thing. So we, as a development, we used more thicker and stronger plastic.
Yeah. So that's what we do in chemistry. We try things out, we run our risk assessments, we make sure it's safe so that it's all good to go. Here, you can see some light. There is the shield volcano that we built over here. There's the manganate core, which is that black purple. I'm going to put some glycerin as fuel. That should get the reaction going, and then it'll cause the dichromate volcano to explode. Okay, here we go. Also, after that, I'm going to place the shield right over here in front of it, and then drop the fume hood shield. Okay, so let's have a go. So that's the manganate going off. And that's the dichromate volcano. Let's see if we made Jeju green again. You can see, it's a little bit, you can see the green volcano that you see over there. It's formed this big caldera. It's green again. We can grow all the halabong we want. So thank you very much for listening, and hope you enjoy Chemistry Week.
All right, good morning, okay. It is good to help people to understand why do we need to study chemistry. Chemistry is a very exciting subject because it's a very colorful subject. And one of the area, chemists, they often have lots of wonderful experiment is a color change, okay? So there are many factors that will affect the rate of a chemical reaction. And today, we're going to do a demonstration which will be performed by 3 Year 9 students. Jaden, raise your hand. Good. Okay, and Philip, raise your hand. Excellent, and followed by Jisoo. Okay, thanks for helping with the experiment, okay? And the factor we are going to look at is the effect of concentration of reactant on the rate of a chemical reaction. All right, let's take a look. I would like to have this, all the students here perform this experiment. It's called the iodine clock reaction. So what happened here is that when you mix a solution to two solutions, I call solution A and B, and after you mix, then you start the timer, and we're going to take a look at how much time you will take for the solution to change color to a blue-black color. Okay? So this is the chemical equation for the reaction. Okay? No worry about all the formula. I call this solution A. This particular type of chemical, and this is solution B. And after the reaction, you produce iodine. Iodine is an element. All right, then you may ask, why it will change blue-black in color? It's because of this. The iodine produced will react with the starch in the reaction mixture in the form of blue-black complex. Okay? All right, here's the experimental setup. So, over there, each student will be responsible to for just one concentration of solution A. Okay? So we have a high concentration, I call 3x, of a medium concentration, I call it x, and of a low concentration, 0.5x. And then you have a start solution in the reaction mixture, also solution B, okay, in the reaction mixture. So the total volume of the reaction mixture will be constant, because this will help us to understand, okay, it is a fair experiment. So that's why we keep the total volume of the reaction mixture constant. All right, this is solution A with a low concentration. Okay, so are you ready?
Yes.
Okay, can you do now? Make sure you use the glass rod to stir. Okay, wonderful. I'll start the timer. Make sure you stir. Okay, good. Okay, take out the glass rod. I already start the timer. So let's take a look. How long do you think you would? How many seconds do you think you'll be able to see the color change?
3 minutes.
3 minutes. Let's take a look. Okay. Right now it's according to the stopwatch. How many? Oh, right there. Stop. Oh, excellent. Guess what? Don't worry about these numbers. How many seconds?
26.
26 seconds. Wow, that's pretty fast. Could you? Low concentration, 26 seconds. Yeah, go ahead. I start the timer. Stir it. Make sure you stir it. 1, 2, 3. Okay, take out the glass rod. Let's take a look whether Philip's prediction is correct or incorrect. Okay. Oh! Oh boy, look at this. Don't worry about those digits. How many seconds? 15 seconds. Could you write 15 here? That's pretty amazing, dude. Use the glass rod. Stir. 1, 2, 3, 4, 5. Okay, take out the glass rod. Oh! Wow, look at this. Don't worry about this. How many seconds?
9 seconds.
Yeah, 9 seconds. Okay, could you write 9 seconds here? All right, let me offer you a very concise explanation using the collision model or collision field. Okay, when you increase the concentration of the reactant, okay, there will be more reactant molecules present in per unit volume. Okay, just like is it very crowded or is it very? If it's low concentration, it's not too crowded. Okay, so when it's very crowded, okay, that means high concentration. You increase the collision. Collision means they're hitting each other. Increase the frequency of effective collision. And that will help to produce the products. And that is a very simple explanation. All right, so thank you very much for your participation, okay? I'll see you next time.
Sweet. So right now in front of me, we have a flame bubbles experiment set up. So there's a bucket of water with some detergent. And as you probably would have seen it earlier on the film, my helpful buddy Korai was stirring the water around so that we can get some bubbles forming. Once the bubbles form, we add LPG gas straight from the tap, and then hopefully more flammable gases will be formed, as you will see earlier, and then we'll set it on fire, and then we'll see what sort of flames will be produced when the gas bubbles are lit with flame. As you can see right now, the bubbles are being formed. These bubbles don't form well if there's no detergent, so that's the reason why we have added in the detergent. That's probably enough. Turn the gas off. Take this away. Make sure the gas is turned off. And then from a safety distance, we set a split on fire. Thanks, Mr. Gomish. And then we stand it fire, making sure that there's nothing burnable around the side. Flammable. Thank you. We just simply put the flame on there. And that's it. Thank you very much. Yeah, I think that's enough. Turn it off.
If you move the ruler.
And then if you can turn off the lights. And then here's a new ruler with the sprint, guys. Make sure the gas is turned off, please, at the side. Make sure you guys step back quite far away. And make sure that you guys point at the sprint where the bubbles were. And that's it.
Whoa! Whoa! That's enough?
Yeah, I'll bet more if you guys want to.
Oh, one more? Okay.
Yeah, you can do more. Go on. Put it under. Move it around as you do it. There you go.
There you go. Yep.
Gas off.
Thank you. And here is a splint. It's not on fire because it's away, and then make sure you guys point at the.
So, my reaction here is a disproportionation reaction. You can see up here. And disproportionation occurs when you get a chemical that's oxidized and reduced at the same time. And hydrogen peroxide, this chemical here, it's H2O2, is a very famous example that's in our syllabus and everyone needs to know. So I'm going to show you this. And we're going to look hydrogen peroxide to break down. And it forms water and oxygen. To cause that to happen, we can either use a catalyst or a chemical that will react with it. And I'm going to show you different chemicals, different catalysts that will they will react and cause that reaction to happen at different rates. Okay, so we'll start with magnesium oxide and see if that reacts at all. Okay, so magnesium oxide, you can see here it's a white powder, and we'll put some into here. The hydrogen peroxide is already in here, and it looks like water. Chemical formula H2O2. Okay, so we'll just put some into here. Okay, so if we look at this here, I can't see any evidence there of a chemical reaction. So zinc oxide, let's have a look. Zinc oxide looks very similar to magnesium oxide, and I'll see if this can cause that reaction up there. H2O, zinc oxide. Again, I cannot see any sign of a chemical reaction. What I should be seeing is bubbles because oxygen gas is formed, right? I should be seeing bubbles. Okay, we're going to move on. Potassium iodide. We'll try this one. Okay, potassium iodide. It looks quite similar, white powder to the other two, and we'll see what this one does. Okay. Oh. Now we've got something happening straight away here. Bubbles being produced. So it's forming oxygen gas. And that reaction is starting to happen. And the color, you can see it's changing color there. What do you think is causing the color change? This is potassium iodide. So it's actually forming iodine. And that is causing the color change there. And the bubbles are oxygen gas. Okay. Right, I'm moving on. Copper sulfate. It's a beautiful blue. Okay, copper sulfate. Put some into here. You can see. Not much going on there. Oh, I can see if I look very closely, there is some bubbles in solution. I can see it's getting a little cloudy there. That's formation of bubbles in solution. And I'll come back to that one a little bit later. Iron sulfate. This is a powder, very slightly green. Let's see here. Oh, look at this one. Here, again, bubbles have been produced. Maybe not quite as. So this one, wow, this one's very exothermic. And you can see this steam here. This is water vapor coming off. So you can see one of the products on the reaction is water. It's so hot it's coming off as a vapor. And let's add a bit more, as much as I can here. There we go. Let's see if we can get a bit more of that steam directed off a bit more.
We're preparing some wash. So in both of these,
Get rid of all. Well, the best way is for that, unless we just put all that in.
Evaporate.
yeah, I know. Okay. So we've got 9. Okay, so we've got in here, we've got 0.5 grams of iodine, which both of you have nicely crushed for me, okay? So we've got...
A bit less than that.
That's okay, that's okay. All right, and then in goes my 4 centimeters cubed of my very smelly ammonia. Now at this stage it's okay, I can stir it because I really want to try and get, this is looking better. Okay, I want a good mix of, I'm trying to get my powder well and truly dissolving, okay? So we can stir this around. There's still a few big clumps of iodine. Can you see, guys? It's already much more making a paste. Yeah? Okay, and obviously when I filter off the excess, okay, so now I filtered now. Because this has got some of the powder on it, okay, this is still potentially explosive. So to get rid of it, we have a little bottle that we've pre-prepared with the wash, okay? So I'm literally gonna put that in and I'm gonna wash it because I need to make sure now that this is gonna be safe to handle, okay? So now that's clean, okay? And this wash I'm gonna use to clean out my beaker when we're filtrating, okay? So I'm gonna let that run for a second longer because it's quite potent at the moment. And we're gonna give it 5 minutes, okay? So until 7 past. At that point, I'm gonna put it under filtering with the Buckner funnel, okay? So it's under a vacuum filter, all right. Oh, get a crack, Karen.
Oh,
Oh, that's not exciting.
we got it.
Look what that is.
So in this experiment that we've just seen, in the sweet powder explosion experiment, it is basically the gummy bear or the candy worm that we have basically coated with sugar and then heated with potassium chlorate. So that's the chemical that was used here, potassium chlorate. So what happens is that this compound actually has a break in the molecule, and then due to the decomposition of the molecule due to the heating, it basically is able to break down the sugar from the gummy bear, or in our case the candy worm, and thus we got a very explosive reaction. It is an exothermic reaction that is purely because of all the energy that was stored in the sugar, and that is what is coming out due to the reaction with potassium chlorate. What we did in the experiment was actually heat the potassium chlorate, and when you heat the potassium chlorate with the Bunsen burner, you break down the potassium chlorate into smaller compounds, as you saw in the presentation earlier, and then once you have taken the decomposed potassium chlorate into the fume hood and then put the candy worm, you get that very explosive, very exothermic reaction called the
candy worm explosion, the sweet powder explosion, or the gummy bear sacrifice. Hoping to see it completely melted, yes.
Something broke.
Twist tube. I mean the
The tip broke. Was it meant to break?